Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, regarding their ability to follow instructions and respond to user queries. A crucial part of training these models is instruction tuning, which often relies on human-curated datasets. However, gathering this human-generated data is expensive and time-consuming, and its quality is limited by human capabilities. The super-alignment challenge seeks to control potentially super-intelligent ICE, which can act beyond our judgment. To address this, we explore reducing dependence on human-labeled data. OpenAI's super-alignment research question aims to prevent super-intelligent ICE from acting unpredictably, which poses challenges for current methods that rely on mimicking human behavior or feedback. One promising solution is self-judging by the AI, where the model can autonomously improve through an iterative self-rewarding mechanism. This involves the model acting as both an actor, producing responses, and a judge, evaluating those responses and assigning scores. The actor's goal is to maximize its score, enhancing its ability to follow instructions in line with human expectations. We believe a limitation of previous approaches is that they focus on improving the actor's response generation while neglecting the judge's evaluation skills. If the judge's ability does not improve, the actor may quickly reach a performance ceiling or even exploit the reward system. Therefore, it is essential to enhance the model's judging capabilities alongside its acting skills. In our paper, we introduce a new self-rewarding method called meta-rewarding, which aims to improve the model's judging skills. We add a third role, the meta-judge, which evaluates the judge's assessments. This allows us to create training data that includes preference pairs of judgments, in addition to the usual preferences between actor responses. All three roles, actor, judge, and meta-judge, are performed by the same model, ensuring a self-improving process that does not require human data. The meta-judge uses a pairwise comparison method to evaluate the judge's judgments, allowing us to compute scores that help refine the training data further. Additionally, we tackle the issue of length bias in the judging process, where longer responses are often favored. To mitigate this, we combine the judge's score with length information to ensure that shorter responses are selected when scores are close. In our experiments with the Llama 3-8B instruct model, we observe significant improvements in performance, particularly in length-controlled scenarios, and our method outperforms standard self-rewarding training. We also see similar enhancements on benchmarks that test the model's ability to answer complex questions. Section Summary. In this section, we discuss the development of a novel self-rewarding method called meta-rewarding, which introduces a third role, the meta-judge, to enhance both the judging and acting capabilities of a language model without relying on human data. By allowing the model to evaluate its own judgments, we aim to improve instruction following abilities while addressing issues like length bias in responses, leading to significant performance improvements in various benchmarks. Section: Meta-rewarding. In this section, we outline our method called meta-rewarding. We start with an initial seed model, which is an instruction-tuned language model, and we do not use any additional human-supervised training data. Our approach involves generating training data through a self-play process where the model takes on three roles. As an actor, it creates responses to prompts. As a judge, it evaluates and scores its own responses, and as a meta-judge, it assesses the quality of its own evaluations. Our main goal is to train the actor to produce better responses to user queries, but this depends on the judge's accuracy. As the judge improves, it provides better feedback, which helps the actor enhance its performance. Thus, meta-rewarding aims to boost the model's abilities as both actor and judge during training. The meta-judge's role is to give feedback that helps train the judge. At a high level, our method is an iterative training process that begins with the seed model, which performs all three roles. Each iteration starts with the actor generating several response variations for each prompt. Next, the judge evaluates these responses using a specific prompt and assigns scores. These scores help us create preference pairs of responses for training the actor. For the judge's training, we select one response and have the Meta-Judge compare two of its judgment variations to see which is better, using another specific prompt. This allows us to form preference pairs of judgments for training the judge. Once we have preference data for both the actor and the judge, we apply preference optimization using a method called DPO, which we chose for its simplicity and stability. After training, we obtain an improved model that we can use for the next iteration, both for generating training data and as the starting model for optimization. We will now detail the process of creating preference data. For the actor preference dataset, we follow a pipeline with a key modification to include a length control mechanism. This change is crucial for preventing responses from becoming excessively long and improving the win rate based on length control. The dataset creation involves three main steps. First, we sample responses from the actor. For each prompt, we generate multiple different responses by sampling from the current model. Second, we aggregate multiple judgments. For each response, we create several judgments using a prompt that instructs the model to evaluate the response according to a fixed rubric, providing reasoning and a score out of 5. We then average the valid scores to determine the final reward score for each response. Lastly, we select preference data with length control. Previous methods simply chose the highest and lowest scored responses as preference pairs, which led to longer responses over time due to the judge's length bias. To address this, we introduce a length control mechanism. We define a quality tier parameter to balance score selection and length consideration. We select the shortest response within the top scoring tier as the chosen response and the longest response within a lower scoring range as the rejected response. If we set the parameter to 0, we revert to purely score-based selection. Section Summary. In this section, we describe our meta-rewarding method, which utilizes an initial seed model to generate training data through an iterative self-play process where the model acts as an actor, judge, and meta-judge. We focus on improving the actor's response quality by enhancing the judge's accuracy, employing a length control mechanism to prevent response lengthening during preference data selection, ultimately leading to a more effective model. Section: Judge Preference Dataset Creation. In this section, we describe how we create the judge preference dataset. Instead of using a judge that gives score-based evaluations, we design a meta-judge that compares two judgments directly. We follow three main steps to generate and select pairs of judgments while minimizing positional bias. First, for response selection, we focus on responses where the judge shows the most uncertainty, indicated by the variance in scores given. We calculate the score variance for each response and select the one with the highest variance for each prompt. If there are ties, we choose randomly. Next, in the pairwise meta-judge evaluation step, we evaluate pairs of judgments for each selected response. We use a prompt that includes the original prompt, the response, and the two judgments. The meta-judge generates reasoning and selects the better judgment. To avoid bias from the order of judgments, we prompt the model twice, switching the order, and we apply weighted scoring based on which position wins more often. We define the results of a judgment pair as a battle matrix, which combines the outcomes of these evaluations. We then calculate the LO score for each judgment, which helps us understand their quality while accounting for positional bias. We select the chosen and rejected judgments based on the highest and lowest LO scores, respectively, again breaking ties randomly. We also notice that the meta-judge can favor longer judgments, leading to chosen judgments being longer on average. To address this, we filter out pairs where the chosen judgment exceeds a certain length, ensuring a balance between quality and conciseness. For our experiments, we use the instruction fine-tuned Llama 3-8B instruct model and follow a specific setup. Before the meta-rewarding training, we perform supervised fine-tuning on a dataset that helps the model learn to act as a judge. We refer to this as SFT. During the meta-rewarding iterations, we utilize 20,000 prompts generated by another model and sample 5,000 prompts for each of the 4 iterations. Each iteration involves training the model on preference pairs generated from the previous model, progressively refining its performance. We generate multiple response variations for each prompt and filter out duplicates, ensuring a diverse set of judgments for evaluation. Section Summary. In this section, we describe our method for creating a judge preference dataset by employing a meta-judge that evaluates pairs of judgments based on their score variance, while addressing positional and length biases. We utilize an iterative training process with a seed model to refine our meta-rewarding approach, ensuring that the selected judgments maintain a balance between quality and conciseness. Section: Evaluation Methods. In this section, we evaluate meta-rewarding by examining its performance as both an actor and a judge. We also compare it to a self-rewarding baseline under the same conditions, using a length control mechanism. This comparison helps us assess the benefits of the judge training data generated through meta-rewarding. For the actor's instruction following, we utilize 3 established auto-evaluation benchmarks based on GPT-4 as a judge: Alpaca Eval, Arena Hard, and MT Bench. Alpaca Eval focuses on chat scenarios with a variety of daily questions. Arena Hard presents more complex questions that meet several criteria across 7 aspects, such as creativity and problem solving, and it shows a strong correlation with chatbot arena benchmarks. MT Bench evaluates the model's ability in multi-turn conversations across 8 question categories. To assess the judge's reward modeling, we measure how well our judge scores align with human preferences and a strong AI judge when human labels are unavailable. We calculate the Spearman correlation and agreement between our model's rankings and the human-labeled preferences from the Open Assistant dataset, using a sample of 190 prompts with 580 responses. We also evaluate the judge's performance on ranking responses from the seed model, which is more aligned with the training data, using GPT-4 as a proxy for human preferences. Our results show that meta-rewarding significantly enhances the win rate. For instance, in the Alpaca Eval benchmark, we observe an increase in the length-controlled win rate from 22.9% to 39.4%, surpassing GPT-4 and nearing the Claude Opus model, despite our model having only 8 billion parameters and not using additional human data beyond the seed model. We also outperform the SPPO baseline, which, while using a strong external reward model, achieves a slightly lower win rate. The importance of the meta-judge and length control mechanism is evident, as the self-rewarding baseline with length control shows some improvement but less so in later iterations. Our analysis of the average response length indicates that it remains stable throughout training, confirming the effectiveness of our length control methods. Meta-rewarding enhances performance across nearly all instruction categories. We break down the 805 questions in Alpaca Eval into 18 categories and find significant improvements in most, particularly in knowledge-intensive areas like science and literature. However, categories such as travel and mathematics show only slight improvements. When evaluating complex questions with Arena Hard, we see consistent improvements across all iterations, with an overall score increase of 8.5% compared to the seed model. This further supports the effectiveness of our approach. Finally, we assess the impact on multi-turn conversation ability through MT Bench. Our results indicate that meta-rewarding improves the Turn 1 score significantly while maintaining a minimal sacrifice in Turn 2 score, outperforming the self-rewarding approach, which typically incurs a larger penalty in Turn 2. Section Summary. In this section, we evaluate the performance of meta-rewarding as both an actor and a judge, comparing it to a self-rewarding baseline, and find that our method significantly improves instruction following and the ability to answer complex questions across various benchmarks, while maintaining multi-turn conversation capabilities. Our results demonstrate substantial gains in win rates and performance metrics, highlighting the effectiveness of the meta-judge and length control mechanisms in enhancing model performance. Section: Reward Modeling Evaluation. In this section, we evaluate how accurately our models judge responses generated by the Llama 3 to 8B instruct seed model. Without human labels, we assess the correlation between our model and the leading judge model, GPT-41106 Preview. Our analysis involves two slightly different setups, mainly differing in how they handle ties from the judge models. We start with a fixed set of Open Assistant prompts that do not overlap with our training prompts. In the GPT-4 chosen pairs setup, we generate two responses for each prompt using the seed model. We then create preference labels with the GPT-4 judge, using a prompt from Alpaca-Eval. To reduce positional bias, we make two judgments by switching the positions of the responses and keep only the data where both judgments agree, resulting in 170 pairs with preference labels. We then use our model to predict rankings for these pairs, generating 11 judgments and averaging the scores. We calculate two metrics: agreement, counting ties as half, and agreement without ties, removing all ties from the weaker judge. In the self-chosen pairs setup, we generate 7 responses from the seed model and rank them using our target model, again averaging 11 judgments. We select the highest and lowest scoring responses as the predicted chosen and rejected pairs, respectively, and perform the same judgment with the strong GPT-4 model, reporting both agreement metrics. Our analysis shows that the model improves its judging ability after undergoing judge training. We observe significant improvements in correlation between meta-rewarding and the strong GPT-4 judge compared to the self-rewarding baseline in both evaluation settings, especially in the agreement without ties metric. For self-chosen pairs, the improvement reaches over 12% in the second iteration, while in the GPT-4 chosen pairs setting, it exceeds 6%. These results highlight the effectiveness of the meta-rewarding approach in enhancing our model's judgment capabilities, aligning its evaluations more closely with advanced language models like GPT-4. We also examine the correlation of our judge with human-ranked responses from the Open Assistant dataset. Using the same average over 11 judgments, we measure agreement and the average Spearman correlation. Our findings indicate a notable increase in correlation with human judgment, particularly in meta-rewarding LLMs. However, this improvement does not persist in later training iterations, likely due to a shift in the distribution of model-generated responses compared to human responses. In our analysis of the length control mechanism, we find it crucial for balancing comprehensiveness and conciseness in model responses. We compare the last training iteration with different length control parameters and present the results. Using a parameter of 0 means no length control, leading to overly verbose responses and negatively impacting the win rate for self-rewarding LLMs. We also explore training with an external reward model, using the strong Starling ERM34B to select preference pairs. However, we find that it does not improve the win rate of Alpaca-Eval in the first iteration, possibly due to its length bias. After the first iteration of meta-rewarding training, we notice that the meta-judge tends to prefer higher score judgments, significantly shifting the scoring distribution towards the maximum score. We also observe an increasing trend in positional bias during training, especially when comparing judgments with the same score. To investigate changes in the judge score distribution during meta-rewarding training, we use the same validation prompts as in our reward modeling evaluation. We generate 7 responses for each prompt and then create 11 judgments for each response. Our visualizations show that training the judge with the meta-judge increases its likelihood of assigning higher scores. However, we notice that in the first 2 iterations, the judge tends to assign scores like 4.5 or 4.75, even though the scores should be whole numbers. While these high scores provide more granularity for distinguishing response quality, they deviate from the expected scoring instructions. Section Summary. In this section, we evaluate our model's judging accuracy by comparing their performance against the strong GPT-4 judge using preference labels generated from responses of the Llama 3 to 8B instruct model. Our findings indicate that the meta-rewarding methodology significantly enhances the model's judgment capabilities, improving correlation with both GPT-4 and human rankings, although some improvements diminish in later training iterations due to distribution shifts in generated responses. Section: Related Work. In this section, we discuss the significant efforts made to align large language models, LLMs, with human values. We can categorize these alignment strategies into two main types: those that use a reward model based on human preferences and those that directly utilize preference datasets. Some approaches train a fixed reward model from human data and then apply reinforcement learning, like proximal policy optimization, to improve the model. To cut down on engineering costs, P3O introduced a contrastive policy gradient that performs better than PPO without needing a value function. On the other hand, methods like direct preference optimization skip the reward model altogether and train the LLM directly using human preferences. Iterative DPO enhances results by using a reward model to generate preference data from model responses over several training rounds. We also note that using LLMs as judges for evaluation and training reward models has become common practice. Some studies have explored how to create datasets for training these judges, but they often rely on human data or data from stronger models. Our approach, however, focuses on improving judgment skills through self-assessment. The concept of superalignment refers to aligning highly capable models that may exceed human abilities. Current AI alignment methods mainly depend on supervised fine-tuning with human demonstrations or reinforcement learning from human feedback, which limits their effectiveness since humans can't always provide useful guidance on complex tasks. There are promising avenues towards superalignment, such as using models to aid human supervision and automatically identifying problematic behaviors. A closely related direction to our work is RLAIF, where AI generates feedback to train other AI. For instance, constitutional AI employs an LLM to refine responses and train a reward model, which is then used for further training. We build upon the concept of self-rewarding, where the model evaluates its own responses, and this feedback is used for preference optimization. However, we have noticed that less attention has been given to training both the actor and the judge simultaneously during self-improvement. We acknowledge some limitations in our experimental setup, particularly the 5-point judging system we adopted. This scoring often leads to ties due to slight quality differences, requiring careful averaging to distinguish between responses. As training progressed, responses tended to score closer to the maximum, making it harder to identify improvements. A more detailed scoring system or a comparison-based approach could help address these challenges. Another limitation is the training process for the judge. Despite our attempts to reduce positional bias, it remains an issue that affected our results in iteration 3. The judge also tended to give higher scores, which led to score saturation and reduced its ability to differentiate between responses. Additionally, the judge showed limited improvement in assessing non-self-generated responses. We believe that addressing these issues could significantly enhance the effectiveness of our approach.